Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 20th, 2026, just 2 days ago. It introduces a new framework called Reinforced Agent Merging that solves a critical mismatch in how reinforcement learning models are combined, allowing a merged generalist model to score about 71 on tool use tasks, significantly beating the specialized agent score of 58. The paper is titled Behavior Knowledge Merge in Reinforced Agentic Models. And as we'll see later, this approach effectively unlocks synergistic potential among agents, creating a unified model that is greater than the sum of its parts. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 presents a radar chart comparing performance across 12 tasks. It covers 3 main domains: memory at the top, tool use on the left, and coding on the right. The solid red line represents the proposed RAM plus method. It forms the outermost shape, which is key because it shows that RAM plus outperforms standard merging baselines, and even beats the specialized agents, shown as dashed lines. Now, Figure 3 breaks down why standard merging fails, illustrating a phenomenon called signal dilution. Each row analyzes the unique parameters for a specific agent: coding at the top, tool use in the middle, and memory at the bottom. Focusing on the top coding graph, the orange bar shows that the full unique task vector boosts coding performance by nearly 24%. However, the light blue bar simulates what happens during standard merging, where this signal is averaged with 2 other agents, effectively cutting its strength to 1/3. You can see the performance gain slumps to about 13%. Meanwhile, the small bars in the center show that these unique parameters barely affect the other tasks, proving that diluting them hurts the primary skill without preventing any real conflict. To understand the structural reasons behind this dilution, Figure 2 maps out the density and spatial distribution of the reinforced task vectors. The left chart reveals a massive disparity in sparsity. Notice the coding agent on the far left. It updates only 3.2% of the parameters, whereas the tool and memory agents modify nearly half the model. Shifting to the right, the stacked bars categorize these updates by how much they overlap with other tasks. The red sections at the bottom represent unique parameters that are not touched by any other agent. While the tool and memory tasks have large unique footprints of over 40%, the coding task has a tiny unique region, meaning its sparse updates are almost entirely entangled with the other domains. Alright, Figure 4 presents the complete Reinforced Agent Merging Framework, or RAM, designed to fix that dilution issue. Starting on the left in panel A, we see the base model trained into separate agents, generating distinct task vectors. Next, in the middle panel B, the method probes these vectors to classify every parameter update. It distinguishes between shared subsets shown in red, where multiple agents overlap, and unique subsets in green, where only one agent is active. Finally, panel C illustrates the selective merging strategy. The shared parameters are averaged to find a consensus, while the unique green parameters are preserved and rescaled. This ensures the merged model retains specific capabilities that would otherwise be washed out. So, Table 1 details the quantitative results across the 3 domains: coding, tool use, and memory. The middle rows list standard merging baselines, including task arithmetic and DARE. Below them, the bottom rows present the proposed RAM and RAM plus methods. Focusing on the final average column, RAM plus achieves a top score of about 66.6, clearly surpassing the best baseline, DARE plus task arithmetic, which scores 63.3. Even more impressive is that the merged model often beats the specialized agents themselves. For instance, in the tool using section under the parallel multiple column, RAM plus hits 70.8, significantly jumping past the dedicated tool agent, which only reached 58.3. Wrapping up, the key takeaway is that standard merging hurts reinforcement learning models by diluting their sparse, unique signals. By identifying and rescaling these unique updates, this framework proves we can build a unified generalist that actually outperforms specialized agents. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.